Good morning, everyone. Welcome to Hadoop and Cloud Storage, Object Store Integration in Production. My name is Chris Naroff. I'm an Apache Hadoop committer and PMC member. I mostly work on HDFS and also alternative file systems like WASB, which is backed by Azure's blob storage, and S3A, which is backed by AWS S3. And that'll be our primary focus for the talk today. I've been a Hadoop user since 2010.
Hi, I'm Rajesh Balamohan. I'm a Thais committer as well as a PMC member. I've been mainly concentrating on the performance aspects of Thais and have been using Hadoop for quite some time.
We also want to acknowledge the work of someone who couldn't join us today, Steve Loughran. He's an Apache Hadoop committer and PMC member. He's been using Hadoop since 2008, and he's done a lot of work around cloud integration. In fact, judging by my Jira notifications, he's working on it right now. Our agenda for today, we're going to start by talking briefly about Hadoop and cloud storage integration use cases. From there, we'll talk about the Hadoop-compatible file system architecture, which is the means by which Hadoop supports retargeting applications to different file system implementations. From there, we'll move into a specific case study about S3A, the file system backed by AWS S3. Then we'll switch over to Rajesh, who's going to talk about Hive's access patterns when it's using S3A, some recent performance improvements that have gone into S3 and the rest of the stack, and there are some TPC DS benchmarks that we're going to share that show some interesting results. We'll conclude by talking about next steps for S3A, what you can expect next. This slide is something that we already saw today, actually. This was used in Sanjay's keynote, so I won't spend a lot of time here. I'm going to try standing in a different spot to see if that makes a difference. I won't repeat this a lot, but I think I would conclude that Hadoop deployment in the cloud makes sense for a lot of the same reasons that just about any kind of application deployment in the cloud makes sense. A lot of the reasons listed here, discussed by Sanjay, they all make maybe even more sense for a clustered technology like Hadoop that involves coordinating a lot of different nodes. This slide is depicting an evolution of cloud storage integration patterns for Hadoop. And cloud storage is a very different model from the traditional HDFS model in a lot of ways. So it has required people to use some different patterns to use it effectively. I've used a solid black border to indicate deployment architectures that are already used today and already used effectively by people. And then on the right, in the dotted border, I've got something that we want to work towards. Our end goal is closer and closer integration with cloud storage. On the far left, we have a situation where HDFS is acting as the primary storage in a Hadoop cluster. Applications are using HDFS for both input and output. But maybe at some point, the administrators of the cluster looked at the cost-benefit analysis and looked at cloud storage as a viable solution for backup and restore. So we see cloud storage bolted on at the bottom of the architecture there. And backup restore is something that's very easily achieved using Hadoop's discp tool. You can reference a source URI on the HDFS cluster and a destination cluster, a destination URI at S3 or Azure storage. And likewise, on the restore path, you can do vice versa. In the middle, we've got a step moving closer towards direct cloud storage integration. We now have the applications directly reading input from cloud storage, but output is taking a two-step hop through HDFS first and then copying final results to cloud storage. And the reason for this is we're going to see there are differences in semantics between what Hadoop file systems expect, largely the HDFS semantics that were implemented, compared to what cloud storage provides. So as a workaround for that, HDFS is the first write so that you can get the expected semantics, and then final results are being copied to cloud storage. Again, discp is a viable option there. And then on the far right, what we want to evolve towards, direct integration, input and output going directly to cloud storage, for seamless integration. I do still have HDFS in the picture here as an option. And the reason for that is that it could still be valuable as a lower latency option for storage of intermediate data sets If you imagine something like a complex ETL workflow consisting of, say, 5 steps, it may not make sense to output all the intermediate data generated by steps 1 through 4 all the way to cloud storage because it's a longer latency connection compared to a local HDFS instance. So you might do something like put the Hive temp directory on a local HDFS installation, and then once the entire workflow completes, final output is going to cloud storage. However, there are some problems with trying to achieve that end goal on the far right of the prior slide. Cloud object stores primarily are designed for high scale, low cost, geographic distribution, high availability, and because of that, there are some engineering trade-offs. They don't often choose to make exact file system semantics available that are an exact match to something like HDFS. And so as a result, application developers working with cloud storage have become accustomed to writing their applications in a way that are resilient to this. And that way they get the benefits of cloud storage, but their end users don't suffer any ill side effects caused by those differences in semantics. Specifically for Hadoop, some of those challenges arise from eventual consistency. Some cloud storage providers offer an eventually consistent model in opposition to HDFS, which has a strongly consistent model. Due to eventual consistency, it can create some odd side effects like creation of a file and not having it be immediately visible the next time you do a directory listing to find it. Performance characteristics are very different. The traditional Hadoop architecture had HDFS and MapReduce and had the capability of pushing compute to the storage layer locally so you could get the benefits of I/O throughput improvements by local access. Cloud deployment models favor a decoupling of the compute and storage layers. So generally what that means is there will be a longer latency connection to the cloud storage backend in comparison to a local HDFS deployment. Cloud storage was not necessarily designed for file-like access patterns. This manifests in API limitations, and a good example of this is rename. HDFS offers an atomic rename operation that is expected to execute quickly, and applications have been written to expect those semantics. For cloud object storage, we can simulate a rename as something like a copy and a delete, and it provides equivalent functionality, but not the exact same semantics because it's no longer atomic, and if there is a lot of data movement required, it won't be as fast. Our goals for this effort in trying to reach that end state on the far right of the earlier slide, we want to integrate with unique functionality provided by each of the cloud providers. Each cloud provider offers something a little bit different, and we want the capabilities of those cloud providers to be accessible through Hadoop. Optimize each cloud's object store connector. By optimizing at that layer, we improve the situation for the entire ecosystem. And then on the flip side, also optimize upper layers for better integration with clouds in terms of the access patterns that they generate. By looking at code in Hive or Tez or Orc, we can make optimizations that are specific there. Our overall approach to the problem, we want to pursue hiding the problems of eventual consistency from applications. One option for doing this is offloading of metadata to a strongly consistent secondary metadata store. We want to explore more performance optimizations in the connectors. I'll briefly mention an example. Rajesh has a lot of performance details later, but briefly, lazy seek here refers to a recent enhancement to the way S3A file system performs seek operations. We found that for applications that did random access, generated a lot of seeks to different offsets within the same file, they would generate a lot of wasteful, chatty HTTP calls to the S3 backend. And we've been able to optimize that now so that seek is lazy. A seek call simply tracks locally which offset you want next, and then on the next read, we can make an intelligent decision about whether or not data can be read locally from already buffered data, or whether or not a new HTTP call does, in fact, need to be generated. And there have also been upper layer improvements across the entire ecosystem. This includes Hive, Orc, and Tez, and we're continuing to look all over the place for those opportunities. This slide depicts the Hadoop-compatible file system architecture. And this is how Hadoop supports retargeting applications to different file systems without making them change code. At the top layer, we have applications like MapReduce, Hive, and you'll notice I've got HBase off to the side. There is this odd ghostly apparition there, and I'll come back to that. I'll explain why that's a little bit of a special case. In the middle, we have the file system abstraction layer. The applications, when they access the file system, generally don't make calls that are tightly coupled to HDFS or any other specific file system. Instead, they're calling into this abstraction layer, which consists of a few abstract classes and interfaces, like file system, file context, abstract file system. Also existing at that layer, we have something in the Hadoop codebase called the file system specification. And this is a formal specification that describes not only the functionality expected of each file system operation, but also the specific semantics. Things like atomicity fall under the heading of this specification. Below that, we have the file system implementation layer. And this is where different file systems can provide different implementations of those base interfaces. Traditionally, this was HDFS running locally in your data center, but there are other options available now that are connected to different cloud storage providers. Something else happening at this layer is what we call the contract tests. And these are a set of test suites that go hand in hand with the file system specification. Those test suites can be very easily retargeted to different file system implementations. And this is a great way for those implementations to validate that they're providing the expected semantics. Or if they are not providing a complete implementation in some cases, then at least that suite gives them an understanding of specifically what's missing, what might be worked on next. So I'll go through this slide very, very quickly. This is really just the talking points from the prior visual. I'm leaving it here so that it's available offline. The slides will go to SlideShare, and they'll be made available through the Hadoop Summit site, too. This slide is a catalog of current state of the cloud storage connectors that we've got in Hadoop and their various capabilities. For Azure, there is WASB, which is a file system backed by Azure's blob storage. Azure's blob storage offers a strongly consistent model. We've observed good performance from this connector. And as far as we know, it's the most well-tested across a wide range of applications, including HBase. I mentioned HBase earlier was kind of a special case there. That's because HBase in particular has had a dependency on very specific semantics provided by HDFS, and most of the other file system implementations have not exactly matched those semantics in a way that is sufficient for HBase. WASB, as far as I know, is the only one that has been run on HBase successfully. It does this by implementing some additional APIs, things like create non-recursive, simulating an atomic rename by use of blob leases, which are a feature of Azure storage, and that's how they achieve that. ADL is Azure Data Lake. This is another offering in Azure, and it is specifically implemented as targeting the use case of big data analytical workloads. So this one is a little different in that the backend is very specifically targeted at that use case, whereas for the others, they began life targeting the object store use case, and then we've layered the file system semantics on top of that. Amazon Web Services, we have S3A. S3A has an eventually consistent model, but we're interested in exploring ways to hide the effects of that eventual consistency model from applications. I mentioned one way to do this is potentially a strongly consistent secondary store acting as a catalog of the files and the directories that are expected to be in the file system. There have been a lot of performance improvements in progress. Rajesh has a lot of details on that later in the talk. And this one is under a lot of active development in Apache right now. There's a link later in the talk to an umbrella Apache Jira that is tracking all of the enhancements that we're working on in S3 right now. So if you're interested in following the details of that, I do encourage you to sign into Jira and set yourself up as a watcher on that Jira. I've also listed here EMRFS. This is a proprietary implementation used inside Elastic MapReduce clusters. And it provides the option for strong consistency layered on top of the S3 eventual consistency model at an additional cost. It's doing this by use of a strongly consistent secondary metadata store. Relatively new is in Google Cloud Platform, we have GCS. There are mailing list discussions in Apache now about possibly trying to get this contributed. This is interesting in that it comes with multiple configurable consistency policies. So there's a default behavior where the eventually consistent nature of Google Cloud Storage does bubble up to applications, but there are options for a read your writes consistency model by tracking metadata state in memory of that process. So at least within that process, it can expect that its writes are visible on subsequent reads immediately. That wouldn't be sufficient for workloads spanning multiple processes. If you want strong consistency across multiple coordinating processes, then they do also have the option to offload to a strongly consistent metadata store. This connector is also offering good performance, and as I mentioned, there's work underway to try to contribute that back to Apache. For now, it's currently hosted as a Google open source project. Now we're going to move into a case study of specifically the S3A connector. We're going to talk about recent enhancements in functionality and also performance. I mentioned that we want to be able to take advantage of all of the unique capabilities that different cloud providers are offering in their cloud storage offerings. And one aspect of this is AWS offers a lot of different authentication options. And traditionally for S3, we've used what we call basic authentication. And this involves setting up your AWS access key ID and secret access key in Hadoop configuration files. There's also the Hadoop Credential Provider API, which is a way of externalizing not only AWS credentials, but other sensitive passwords in the Hadoop ecosystem into external files rather than putting them into the world-readable configuration files like core site XML. But beyond that, the AWS SDK and the AWS services offer EC2 metadata. And with this model, credentials are provided by AWS directly onto EC2 provisioned VMs. And this is more secure because there isn't really any external distribution of secrets required, either to configuration files or the Hadoop Credential Provider API or anything else. Instead, the EC2 instance can access those credentials locally through access to the EC2 metadata service running locally there. Another option is AWS environment variables. This is a less secure option because environment variables have a tendency to leak out via things like child processes forking and forgetting to scrub the environment, or people attempting to snoop on the /proc file system. Even though it's less secure, we do want all the options available there if somebody finds that an easier integration option. This is something that's provided via the AWS SDK, which is what S3A is using under the hood to make its calls to S3. Another option is session credentials provided by the Amazon Security Token Service. And what's unique about this is the tokens have a limited constrained lifetime chosen at allocation time. So if there were to be something like a credential leak, this would limit the impact because those credentials have an expiration time associated with them. And finally, there's an option for anonymous login. This is something that you can use to very quickly prototype and just start feeling out what it's like to use S3A file system. You can read from anonymous, you can read without credentials from publicly accessible S3 buckets to get data sets from there. Interesting side note, we recently resolved a JIRA from 2008, which is always exciting when you are able to kill those really old bugs. There was a bug in the encoding of the AWS, the secret access key for certain characters for / and plus when they were passed via command line. So if you've ever been bothered by that, check out Hadoop 3.7.3.3, we fixed it. Wow, all right. That is important to someone, good to hear. Next, I want to talk about encryption. S3 offers a server-side encryption option. This is encryption of data at rest after it lands at S3. S3A currently supports the SSE S3 option, whereby S3 will apply a unique encryption key to each object stored there, encrypted using AES 256. This is something that's now also covered in S3A automated test suites. We've been paying attention to trying to really flesh out test suites as well to make sure all of that functionality is well covered. There is also support for additional options under development. S3 also offers the SSE KMS and SSC options. There are Apache JIRAs out there tracking development of that integration. And finally, while we're doing all of this work, we've been trying to pay very much close attention to supportability aspects. So for documentation, we've been trying to backfill a lot of missing documentation so that S3A is better understood by the entire community. And when we release these new enhancements, we're making sure that the patches also include documentation updates to cover those enhancements. This is still to be published on hadoop.apache.org, so if you were to go there right now, you would not find the current content. But I've left a link to the raw content in GitHub, and it's actually not even that raw because GitHub will render the markdown in a pretty nice way. So if you want the most up-to-date documentation on what we've done recently, look there. And again, the slides will be available later, so you don't have to worry about writing down that URL or anything. On error reporting, we've found that in the past, usage of S3A could be difficult to troubleshoot if something went wrong. So what we've done is tried to identify common user errors, such as misconfiguration of credentials, and just provide more helpful error messages to help you figure out what to do next if that happens. We've also looked at the HTTP error codes that are coming back in the S3 responses and tried to map those more intelligently to equivalent exceptions in the Hadoop ecosystem so that those errors could be handled better by applications. There's been a lot of work done on instrumentation too. We now have a lot more internal metrics covering a wide range of the primitive operations that are happening as people call into the file system API. And this is something that's already proven helpful because we were working on one patch, was a performance improvement, and it turned out that it improved performance for one usage pattern, but harmed performance for another usage pattern. And based on those stats, we were able to act on it and come up with a patch that didn't have to sacrifice performance for that other use case. And at this point, I'd like to turn it over to Rajesh for more details on the performance work.
Thanks, Chris. So seek is one of the most expensive calls in the earlier implementations of S3A implementation. So what used to happen in the seek is that we aborted the current connection which is established to S3 and reopened the file and landed up on a specific location for the seek operation. In the case of this gets more pronounced where in the cases of positional read wherein the read doesn't change the offset within the file. What I mean by that is the internal implementation of positional read is something like a seek that is land upon a specific location, read a set of bytes and then seek back to the original location. So if you look at it, for doing a positional read, it would incur 2 connection aborts, and since it is going to be on a HTTPS basis, this is going to be a lot more expensive. So some of the file input formats which were making use of this particular positional read were taking a lot more hit on S3. In the recent implementations, we have fixed this problem wherein we reopen the file only on need basis and made the seek as a totally no-op operation. And the second set of problems is related to the backward seek. For instance, there are some file input formats wherein you can have random seeks. Just to take an example of ORC or in Parquet, you would end up reading the footer information first, which is going to be at the end of the file, and then later go back and then start reading the realistic data contents in the beginning of the file. So the moment it started doing the backward seek, it used to abort the current connection and that incurred a lot of cost. So in the recent versions of S3A file system implementation, we have addressed this problem where you can set the effort wise parameter to either sequential mode or random mode. And the moment you set it to random mode, we exactly read the amount of bytes that is requested for doing the read, and that helps in terms of reducing the overall connection abort problem. Let us look at an application like Hive which is built on this particular layer and figure out how this impacts the overall performance. So at a very high level, if you look at the kind of data access patterns in Hive, it can be classified into 3 categories. One is the ETL or the admin related activities wherein you would bring the data from the external sources, create tables, create some table statistics as well as column statistics in terms of running your queries in the most efficient way and run some commands like MSK and so on. But predominantly it's going to be like more like an admin or a ETL related activity. Once the data is made available to the end users, end users can run a set of queries in terms of doing the data mining activities, and that output can be stored onto a specific location, or even the data or ETL related activities can end up writing the data onto a specific location, but predominantly the write related activities. So, if you have the data which is already located in S3, you would end up creating an external table in terms of accessing that data in Hive. And if the data set is already partitioned, you will have to run an explicit command like MSK, which helps in terms of scanning the entire directories or the tables or directories within the table directory, and it updates the partition related information onto the Hive metastore. That can turn out to be a lot more expensive operation. The reason is based on the number of partitions that you have, it ends up scanning the directory one at a time and then updates the partition related information onto metastore. So, in the recent versions we have parallelized this and reduced the number of total calls to the metastore as well, and figure out that that helps in terms of reducing the total number of or the overall runtime by almost like 3x. And it is extremely important to have the table statistics as well as column statistics populated in the most accurate way in order for the Hive queries to run a lot more efficiently. So, table statistics can easily be gathered by setting the autostats gather enable equal to true in the Hive side, but in order to populate the column statistics, you will have to explicitly run the analyze table column statistics command. So, that was turning out to be a lot more expensive, and that was making a lot of calls to metastore. So, we ended up tuning that and got 3x improvement in terms of the overall response time. Just to give an example, the column statistics computation in catalog returns table in the TPC data set, it used to take almost like 600 seconds earlier. Now it takes only less than 200 seconds or so. The reason why these things are important is that since the data is already located in S3, you would want to figure out what is the easiest time or like the bare minimum time that you want to have in terms of running the query and then getting the output. So, that includes setting the creating the data set or creating the tables, analyzing them and then running the query. So, that is one of the reasons why we ended up tuning all these things. And the moment the data set is available to the end users and when the Hive query starts running, the first and foremost thing that happens is the get split operation. And based on the number of partitions or the files that you need to scan, the get split operation itself could be a lot more expensive. The reason is it has to scan the scanning operation in S3 itself is a lot more expensive one. That is one of the reasons. If you are using file formats like ORC, that provides a set of thread pools in, which can be a lot more helpful in terms of computing the get split operation. It is a tunable parameter, so based on the data size that you are planning to have, you can end up tuning that. ORC also supports different file split strategies. For instance, it supports ETL, it supports BA strategy, it supports hybrid and ACID as well. And if you are using ETL related strategy, the way that it works out is it ends up scanning or it ends up reading the footer information of every file and reads a certain amount of bytes in terms of doing the split pruning activities. So, that can incur a lot of S3A reads. So, one of the good things about this one is that the moment the data is read, it can be cached onto the local cache itself in the VM. So, when you run the query for the second time, it does not touch or it does not read the data again from S3, it will try to figure out the details from the cache itself and then a lot more faster. The reason why this is going to be a lot more useful is that initially people will have or scan a lot more bigger directory or like a bigger data set, let us say 900 partitions or so, and finally they will try to drill down, in which case the second and the third queries is going to run a lot more faster with the cache enabled. And also once the split is computed, it has to run the details on the task side, and as a part of it, it has to reopen the file and then read the footer information again. But if you look at it, we just read the information or footer information on the app master side. So, one of the optimizations could be to just pass on the footer information that we have read in the AM side onto the task side as a part of the split payload itself. That optimization is already in place, but one of the concern was that it was sending a lot more information, because of which the app master itself was running into memory pressures. That has been fixed in the recent releases, and we send bare minimum information, and we do not have a lot more memory pressure on the AM side with this particular setting enabled. Once the split information is computed, Thais, let me step back a little bit. I mean, Hive uses Thais as the default execution engine, and the moment the Hive computes its split information, it passes on this information to Thais side for doing further optimization. And Thais relies on a lot more different parameters, like the min and max split grouping size, which is set to 50 MB as well as 1.5 GB by default, and also it relies on a couple of other additional information like the locality information and so on. And S3 always provides localhost as its locality information. And if you have your overall split length less than the min split group size, Thais is going to do a lot more optimization and end up creating only one split for processing. Just to give an example, let us say you have an inventory table in TP-CDS dataset which has got some, let us say 50 different files, and the overall split length put together is less than the min group's split size. If that is the case, Thais tries to optimize everything together and then give it as a single split. The problem with that approach is, we all know that S3's file reading is going to be a little slower, so only one task will end up reading all the 50 files in a sequential manner and then decode the information and then read it. That's going to be a lot more expensive operation. So this has been fixed in the recent versions of Thais, wherein if Thais doesn't understand the or if it doesn't have enough information about the locality details in the splits, it does not optimize those splits in a lot more aggressive fashion. So that has been fixed in the recent releases, and also we observed that whenever people run queries on the Hive side, I mean the container launches were a lot more slower. So AWS doesn't have the concept of rack locality, in which case you could always set the node locality delay in the capacity scheduler to 0, in which case the container launches were a lot more faster. So with all these settings, we benchmarked using Hive test bench, which is a subset of TP-CDS queries on M4X large machines, and these are general purpose machines on AWS, and we had 200 GB data set on S3. We benchmarked with the previous versions of HDP 2.3 and compared it against the latest version and got around 2.5x improvement in throughput, or like in the response times. One other observation that we had was lots of queries like query number 15, 17, 25 and so on didn't even run in the previous versions of HTTP due to the exceptions that we got from the AWS side. That is, we were getting a lot more AWS timeout exceptions. Good news is that all those queries run perfectly fine in the latest version of HTTP, and also we get 2.5x improvement in terms of the overall response time. Certain queries get a lot more improvement. Just to take an example, query number 22, which used to run in 160 seconds in the earlier case, now can get completed in 10 or 15 seconds now. That's a lot of improvement on certain set of queries. If you need a lot more better performance improvement, you can always run your queries on Hive on LLAP. This graph shows the comparison of the latest HDP with all those optimization in place and how does it work out with Hive on LLAP. In some of the queries, we get almost like 4x improvement in response time, and I'm not going to get into more details on this particular slide. There is an awesome talk by Gopal on Hive on LLAP, so encourage you to attend that particular talk. In terms of best practices, if you have a lot of data to be uploaded onto S3, ensure that you set the multipart threshold as well as the multipart size appropriately. In some cases, you might have to tune the connection timeout as well. The default is set to 200 seconds. Based on your environment, you might want to tune that. Ensure that you set the node locality delay to 0 in the cases of S3. And if you have any storage based authorization enabled in Hive, please use the default one because it doesn't have the concept of storage based authorization in the case of S3. set the pre-event listeners to empty so that it doesn't have a lot of file permission checks and so on. And if you are using ORC, please tune the number of threads that you are going to have for the get splits operation. With that, I'll leave it to Chris. Thank you.
Our next steps for S3A, I mentioned that we have a master JIRA. We don't have a microphone, but we have a master JIRA. We have a master JIRA referenced here that is tracking what we're doing next with S3A. I encourage you to go check that out. We also want to look into the problem of output committers. There's been this problem, long-standing problem of how to handle the output commit phase, which has been heavily reliant on HDFS rename semantics, how to handle that better on cloud storage. A way this might go is an object store abstraction layer. So similar to a file system API, but perhaps something more direct for applications to call for interaction with object stores. So it would avoid some of the impedance mismatch associated with the file system API. And we're going to continue to look into ongoing performance improvements. So summarizing today, we talked about an evolution of Hadoop integration towards cloud storage. We talked about how the Hadoop-compatible file system architecture facilitates that. We talked about how we now have support for integration with multiple cloud providers. We looked specifically at S3A as a case study for recent enhancements. We showed performance improvements in Hive and also using TPC DS benchmarks. And we talked about more of what's coming soon. So thank you, everyone. We'll open it up for Q&A now.
What about the security, the Ranger extension onto the object storage? We are having a tough time with, we are almost there virtualization on the object storage, the object storage concern. So, but I think there are some limitations like Ranger cannot extend security policies to the object storage. That's the first question. The second is, you talked about the ORC, all the comments related to the benchmark record of ORC. What about the part K?
OK, I'll respond to the first question. The first question was, what about Ranger integration when you're integrating with S3 or other cloud storage? And that's actually a really great question, and I was not specifically thinking of that. I don't have a prepared response for you. Ranger typically integrates with file system authorization by hooking into HDFS at the name node layer. I'm not aware of any specific work happening in Ranger around there. Yes, and there was a talk about that yesterday. So if you didn't go to that talk, watch for the video for that talk too. And for the second question, I'll go to you, Rajesh.
So yeah, we are not used Parquet for our internal benchmarks. So that is something in the pipeline that we'll have to carry out in the next couple of weeks or so.
How about comparing HDFS performance with for example, S3? Did you guys do any work on that side?
So are you referring to the on-prem HDFS performance, or is it going to be the HDFS performance in the cloud itself?
Same reasons as just running your, for example, Hive TPCH benchmark on top of HDFS and then comparing what the numbers are.
It's going to be a little slower when compared to the HDFS. We are not completely measured or like enhanced the performance on that aspects. But yeah, we'll have to do that.
To get the best performance out of S3, the standard, there are some best practices that AWS has published, which is you have to randomize the keys so that S3 actually uses the keys to allocate the objects to the partition. So if you want to get maximum throughput, because S3 is a multi-tenant system, so another thing is you want to make sure that objects are not too small, not too big. You know, those things are a little harder to do with S3, but given that you guys are moving to metadata store, are these kind of performance improvements possible?
Yeah, I'll quickly repeat the question. The question is, there are certain best practices around S3 performance, and some of those seem to be contradictory to file system access patterns. So you have a set of file names that are likely to have common prefixes, and there are recommendations around sticking random prefixes in front of objects to randomize. And I think you really anticipated my answer to that too, which is we're thinking about the external metadata store as an option for enforcing strong consistency. We also see it as an option for a kind of caching layer and possibly something that can satisfy those lookups more quickly. And we're out of time at this point, but if you have any other questions, definitely track us down outside. Thank you.
Thank you.